Well, we've made it through the introductory part with fractions. We've explored all the different models, ways to convert between different forms of fractions. And now we're going to apply all of that learning that we just did into doing the operations with fractions. And I'm sure that in the past, you've learned how to add and subtract fractions, how to multiply and divide. You've learned the processes, the procedures, the algorithms. But of course, we're going to be exploring now way more in depth why all those things work using all the models that we are familiar with. So let's go ahead and get started with that. Of course, for this section, we are going to first look at just our overview. And you're going to see that we're going to talk about addition and subtraction, those denominators, mixed numbers, multiplication, certain versions of that. Again, we're going to model that with manipulatives and drawings. We're going to get into division and then number properties, those ones that we've seen before with whole numbers and integers. We're going to revisit all of those again. We're also going to add in a new one, the inverse for addition and multiplication. And then we're going to get to our mental calculations and approximations. Again, a lot of the same strategies that we've seen before. And so we won't spend too much time on there, but there are some really interesting ones that I think maybe you've never seen before, maybe you've never thought of. And my hope is that your eyes get opened a little bit to some of the options that exist that you may not have been familiar with. So let's do that. So to start this, we will look at a scenario, an application, a story problem. It says, suppose that parts of 2 school days are used for a national testing program. 1/3 of a day is required for test A, and 1/5 of a day is required for test B. Approximately what part of a whole day is used for testing? And so, like I said, we're going to be looking at our traditional models that we've been learning about. And this helps illustrate what's really going on here. If you look at this yellow bar, what you'll notice is it is the 1/3 of a day, right? This shaded area is showing us that 1/3 of a day. So from here to here is 1 day. And this shaded part is 1/3 of it. And then it says 1/5 of another day, 1/5 of the day, which we see right here, is required for test B. So this is a demonstration of addition. And when we line up the end of the third, and then we put that beginning of a fifth right there, what we're looking for then is, well, what is this amount, right? What is this amount if we combine those two, right? From here over to here. And you can see it is pretty close to a half, pretty close to a half of a day. But we actually don't know exactly, right? We don't know if it's exactly a half or if it's close. But this model shows us that, again, if we line up 1/3 here, 1/5 there, we combine them, it will be approximately 1/2. And so that's the very first model that we look at. Can we look at those shaded fraction bars, line them up, and just sort of examine it, get a visual? And so the next thing we'll talk about is that those fractions did not have a common denominator. And so let's look at a scenario where we do. And so for this one, we are going to add these 2 fractions, and we're going to model it with those fraction bars. So the problem we will do is 4/6 plus 3/6. Okay. And here is what a similar model would look like. Let me enlarge that for you. And so let's examine this one and see how it relates to the previous question. So this bar on top here is, of course, cut into 1, 2, 3, 4, 5, 6 pieces, as is the bar on the bottom. Why? Because both of our fractions had denominators of 6. So they're both going to be cut up into 6 pieces. It also is important for me to note that the length of these bars, they are the same. So then we look at the shaded sections. We had 1, 2, 3, 4 of them here for the 4/6. And then we had 1, 2, 3 of them here for the 3/6. And then again, if we line up the end of the first one with the beginning of the second one, what we are going to measure then is the distance from here all the way to here. What do we get if we combine them? And if we just count the number of sixths, it's 1, 2, 3, 4, 5, 6, and 7. So it's 7/6. You can also see, if you examine it like a mixed number, this first part from here all the way to here, that would represent one whole. Sorry, from there to there is one whole. And then from here to here is an additional sixth. So 7/6 we can see is equal to 1 and 1/6. So there's a nice visual that also helps illustrate what's happening with that problem. We can also use number lines. We've seen number lines before to help us visualize what's going on when we're doing certain operations. This is no exception. This number line models the fraction 5/8 plus 6/8. 5/8. So if this is 1, this is the number 1, here's 0, and notice it's cut up into eighths. 1, 2, 3, 4, 5, 6, 7, 8 sections. Here's our jump to 5/8. And then to that, we add 6 more eighths. 1, 2, 3, 4, 5, 6. Where do we end up? 1 and 3/8. So there's another model. But again, this only really worked if we were adding fractions that had common denominators, because we then knew how to subdivide our distance from 0 to 1. So let's try just doing some standard fraction calculations, like 4/5 plus 3/5. So go ahead and write that sum as a fraction or as a mixed number if necessary. So whatever approach you took, you should have ended up with 7/5. Again, you're really counting how many fifths there are. 4 here, 3 here, together that makes 7/5. Now, we want to make sure we put that in a mixed number if necessary. And so that would be 1 and 2/5. 5 goes into 7 once with the remainder of 2. Second one, go ahead and try this one. 5/3 plus 2/3. Again, when you add those fractions, you're adding the numerators on top, and you're counting how many thirds there are from that denominator. And so we have 7/3. Now this one, as a mixed number, would be 2, because 3 times 2 is 6, leaving us with one more to get up to 7. 2 and 1/3. So what if the denominators are different, though? Because when they're the same, it's pretty straightforward, just adding those numerators across. So let's take a look at 2/5 plus 1/3. And so I'm going to show you the model of what that would look like the other ones that we did a few moments ago. So let's just examine this in a little more detail. The purple rod on top shows 2/5. We have 1, 2, 3, 4, 5 sections, 2 of which are shaded. On the bottom, the yellow rod is 1/3. 1 out of 1, 2, 3 is shaded. And so what we're trying to find then is the distance from here to about there. And so that's a hard one to estimate. In fact, it's impossible to know just by looking at it, because this line doesn't line up with either of those lines. What we do know is that it's more than 1, 2, 3/5, but it's less than 1, 2, 3, 4/5. So it's somewhere between 3/5 and 4/5. But we can't do it unless we replace the two fractions with fractions having the same denominator. We must get a common denominator. And we spent the whole last video talking about common denominators. So you should feel pretty comfortable with that at this point. Here's what a visual would look like of this scenario. This may take a moment for you to digest, but here's where we started over on the left. And what we're doing here is looking at our denominators, and we see if we cut our figures into 15 pieces, 5 and 3 both have a least common multiple of 15. And so we're going to take each of the, I'll do it over here, each of the thirds, I'm sorry, each of the fifths, right, on top, and cut them into 3 pieces. So every one of the thirds will cut into 3 pieces. Now watch what happens when I do that. Notice how this one lined up right with that yellow bar there. We already have this one, we'll extend it. Look how this automatically is cutting the yellow piece into 5 pieces. 1, 2, 3. I missed that one. 4, 5. 1, 2, 3, 4, 5. And so when we draw those lines straight down through the fifths, we're also cutting up the thirds. And what we end up with would be 15 pieces in total here and 15 pieces in total there. So they're both cut up into 15ths. And then if you just compare the shaded sections right here, from here to here, this has 1, 2, 3, 4, 5, 6 15ths. This yellow one from here to here is 1, 2, 3, 4, 5 15ths. And when we add them, when we combine them, this whole section from there to there would be 11 15ths. So again, there's a really good visual demonstration of what's happening when we're getting common denominators in order to add those fractions. And so here is what I would consider a formal definition then of what it means to add fractions with unlike denominators. One of the things that's important to note is that when you multiply the two denominators together, you'll always get a common denominator, but it's not always going to be the smallest one. And sometimes that's okay. And then once you do have your common denominator, you just add the numerators and keep the denominator. Let's examine this definition and try to make sense of it. This was our starting fraction, a over b plus c over d. It's our sum, the two fractions added together. Notice what happens here in the denominators, right? We have our two fractions, but now they look a little different. B and D were the two different denominators, but now we have BD in both the denominators. This first fraction was multiplied by D and D on top and bottom. The second fraction was multiplied by B and B on the top and the bottom. It doesn't matter if we place it first or second. It doesn't matter the order. Often we'll place them in alphabetical order when they're just variables. But now you notice that we have the same denominator. It's represented through variables. That's okay. Variables are just numbers in disguise. They behave like numbers though. And then to do the sum, we combine the fraction to have the same denominator and we add those two numerators together. So this algebraic definition explains what's really happening when we're adding fractions with unlike denominators. Here is a statement from the Common Core Standards of Mathematics regarding what students need to be able to do in 5th grade. This is a 5th grade standard. And you'll see it is doing what we just did, right? Knowing how to add those fractions with unlike denominators. And what I'll say is that so many things that we've already done in this class to this point lead up to being able to do this task right here. Having an incredible grasp of numbers, understanding factors and multiples, knowing some basic multiplication facts, all those things are crucial for being able to do this exact task right there. So let's try a couple. For you, I'm going to give you 3 of these problems, and then you will pause the video and try to do them on your own. So I have 3 fractions here, and they look like this. So go ahead and pause and try these. So for the first one, again, we've got denominators of 4 and 7. I'm just going to multiply those 2 denominators to get my common denominator. So for this first one, I will do 1 times 7 over 4 times 7 plus, and over here, I'm going to do 3 times 4 over 7 times 4. So this fraction got multiplied by 7, and this one by 4. Let's simplify that to 7 over 28 plus 12 over 28. And now we can add those numerators, 19 over 28. For the second one, we can do the same thing. But what I will note is that you can get a smaller denominator than just multiplying 6 times 8, because they're both divisors or factors of 24. So I'm going to multiply this fraction by 4 and 4, and this fraction by 3 and 3. That will give me 20 over 24 plus negative 3 over 24. Same denominators. Now we can add what it says to do on top. Note that this is a positive plus a negative. That gives us 17 over 24. And finally, there are cases where you can leave one of the denominators alone because it is the greatest common denominator between the two. All we have to do is double the number 10, and then, of course, double the number 7. That gives us 14 over 20 for this one, plus 9 over 20 for this one, for a total of 23 over 20. Did you remember to change that to the mixed number? That would be 1 and 3/20. 20 goes into 23 once, with 3 left over. So let's talk a little bit then about mixed numbers and how we might go about adding mixed numbers. There are different ways to do these. So I'm going to walk you through one, and then I'm going to have you do another. So this is my preferred method, and I think if you have developed good number sense and are making sense of the things we've talked about in this course, and especially in section 5.2, you should be able to make sense of this approach that I'm going to show you right now. Let's say we have 6 2/5, and we're going to add it to 3 4/5. So we're going to stack them on top of each other like that. It's kind of like lining up place values. We line up the fractions, we line up the whole numbers, and then we just add from top to bottom. If I had 2/5 plus 4/5, that is 6/5. And if I had 6 plus 3, I get 9. But you might notice that this fraction, this part of our mixed number, is improper. And that seems a little weird, right? And so what I'm going to do is I'm going to show you a visual of this, okay? And so I'm going to draw as quickly as I can 9 circles. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's our 9, right? And then what I'm going to do is I'm going to draw another circle, and it's going to represent 6/5. So I'm going to cut this into, you know what, I think I'm going to redo that, and I'm going to use a smaller tip on the pen. So we'll draw a circle. We're going to cut it into 5 sections, and we're going to shade 6 of them. So here's 1, here's 2, here's 3, here's 4, here's 5, and we ran out of space. So what do we need to do? Add another one. We saw this in a previous video from the last section. So we draw another one, and then we can shade our 6th wedge, our 6/5. So this part right here shows 6/5. But you'll notice that we shaded in one entire circle. So what we end up with here is a total of 10 completely filled in circles and 1/5 less left over. So this mixed number here simplifies to this. Another way you can think about that is take your 6/5 and change it to 1 1/5, like you normally would do with an improper fraction. And then you add that back to the 9. 9 plus that 1 is going to give you that 10. This is just a visual of what's happening there. So it's your turn to try this one. Let me again change the pen. Number 2, 3 1/2 plus 5 2/3. Take a moment to pause the video and try this on your own. You may have noticed that this one started off where your fractions did not have common denominators. So I'm going to start by doing that right up here. I'm going to multiply these by 3 to get 3/6, and these by 2 to get 4/6. Then I'm going to add the fractions. 3 plus 4 is 7/6. Then I'm going to add the whole numbers. 3 plus 5 is 8. And we have to do the same thing we did over here. If you just focus on the improper fraction portion, you'll notice that that would be equal to 1 1/6. It's kind of like in decimals where you would put the 1/6 here, carry the 1 to the next column, and then add 1 plus 8 to get 9. It's the same thing again when you add decimals and you get more than 10. It's the same idea here. So hopefully you were able to get 9 1/6. Hopefully that is making sense to you. Let's move on to talk about subtraction now. Subtraction is very similar. But it's also important that we keep in mind some of the principles that we learned about back in the whole number chapter when we talked about subtraction. We learned that there were 3 different ways, 3 different concepts for subtraction, 3 different ways we could view it. One, the takeaway, one is the comparison concept, and one is the missing addend concept. So we're going to keep those in mind as we go through these as well. So here's the first one that we will look at. It is 1/2 minus 1/6. Now you could probably do that given what we just talked about with adding fractions, but it's also important that we connect it with a visual model. And so here's what this would look like. And this is going to demonstrate kind of both the comparison concept as well as the missing addend concept. So let's talk through this. The top bar represents 1/2. This is 1/2. We've got a green bar cut into 2 pieces. The bottom bar represents 1/6. And we are subtracting them. And so again, one way to view that is the comparison. Look at how far apart they are. We're really trying to find the difference between them. That's also kind of working us through that missing addend concept. If I had 1/6 and I added some number, it would have to equal 1/2. Here's your 6, we're adding this number, and the total then would be 1/2. And so you can see from this visual that if we line up these middle bars, oh, that works out very nicely. If this is 1/6 right here, then this has to be a 6, and this has to be a 6, making this a total of 2/6. Or if we reduce it, 1/3. This is the same as 1/3 of the entire red bar. So that was there just for you to get a visual representation of what we're doing, right? Why this starts to work. Let's take a look at one more visual. Number lines. This is going to show a model for the subtraction problem, 11/12 minus 7/12. But it's going to show it again using the number line model that we've seen also many times. And so it would look something like this. Again, we always start at our reference point of 0. And the first thing we do is we go out to 11/12. Notice how 0 to 1 is cut up into 11 or 12 sections. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we get to 11/12, but then we back up 7/12. This is the takeaway model. We're taking away 7/12. We go back 7 and we end at 4/12. So those are a couple different models that can be used to visualize what's happening with subtraction. Of course, those were shown using common denominators. So let's view them using unlike denominators. Let's try 5/6 minus 1/4. And so this image that I'm going to show you is going to show what that looks like. So 5/6, again, we can view as this red one on top. 6 sections, 5 of them are shaded. Down here at the bottom, 4 sections, 1 of them is shaded. We're trying to find the difference between those, right? We're trying to find this section. So just by looking at it, if we're trying to measure how big this is, if we know each one of these pieces is 1/6, that means this is 1/6, this is 1/6, this is 1/6, that's 3/6 right there. This would be a 4/6. So our answer has to be somewhere between 3/6 and 4/6, right? It's going to be somewhere in that distance, but we don't know. We can't just guess. So we have to do something very similar to what we did back when we were doing addition. We had to cut them up so they have common denominators. So this should look fairly familiar. In the addition example, we did it with a denominator of 15. Here we're doing it with a denominator of, of 12. And so what you can see here is, again, we're cutting the sixths up into 2 pieces each to get 10/12. The fourths up into 3 pieces each to get 3/12. And then when we try to find the difference between them, we're trying to find the distance from, let me make this real obvious, use a different size. We're trying to find the difference from here up to here, right? We're trying to find that dimension right there. How far is that? And now that we've got them cut up into 12ths, we can count 1, 2, 3, 4, 5, 6, 7. 7/12. And we see that here. These 10 on top minus these 3 on the bottom leaves us with 7 in the middle. So again, hopefully that model is helping you see what's happening. That's what it's all about, right? When you are trying to learn how to do fractions, you have to be able to visualize this. Of course, once we get to grasp the ideas a little bit better, then we can introduce formulas like this, formal definitions. This looks just like the one we saw earlier with addition, except it's subtraction. If you're multiplying the 2 denominators together, it's going to give you that common denominator, and then you adjust the numerators as well and subtract them. So that should look very familiar to you. Let's go ahead and have you try a couple more on your own. So we're going to do 3 subtraction problems with different denominators. And so your job will be to do those calculations. So please pause the video again and attempt these on your own and then come back. So I took the liberty of starting the process for us as we review these. We've talked enough about getting common denominators. You can see my work here, multiplying by 3 and 8 to get 21/24 minus 8/24. That would leave us with 13/24 for this first one. For the second one, I multiplied by 5 and by 2 to get 5/10 minus 8/10, which is -3/10. That's okay, we can have a negative number. Fractions can be negative too. And then here we multiplied by 4 and by 3 to get 8/12 minus -3/12. What you might notice here is that we are subtracting a negative number. And as we learned in section 5.1, we can think about that or even restate it as 8/12 plus 3/12. Subtracting a negative is like taking away debt, which means we are gaining. So this is going to leave us with 11/12. So we've seen addition and mixed numbers. We've seen subtraction. Now let's finish this up with subtraction of mixed numbers. And the thing about subtraction with mixed numbers, again, there are different ways to do it. What we are going to examine is something similar to what we saw when we were adding mixed numbers, but it's kind of in reverse. We actually are going to do a little bit of borrowing or regrouping, but it looks a little different than it does when we're doing with decimals. So I'm going to work one for you first, and then I'll have you try one. So 4 1/5 minus 1 2/5. So if we approach this the same way we approached addition, we would subtract and then subtract. But do you notice that our numerator here is less than this numerator here? We don't have enough to do subtraction with. So just like with decimals, we need to borrow. So we're going to borrow from the 4 and make it a 3. But the question is, what do we do with that 1? Rather than tell you exactly, I'm going to show you. I'm going to show you a little diagram. So we're going to do the same thing we did in the previous addition problems, where I'm going to take 4 1/5, and I'm going to go 1, 2, 3, 4, and then I'm going to take the 1/5, and I'm just going to draw a picture of it. 1/5. So we can agree this represents 4 1/5. But what I'm going to do is I'm going to take one of these circles. I'm going to take this one, and I'm going to redraw it slightly differently. So I'm going to erase it, and then I'm going to redraw it, and I'm going to cut it up into fifths, and I'm going to shade each piece individually. You can agree that's still a completely shaded circle, agreed? It still represents one whole circle. We still have 4 circles and 1/5. But what you'll also notice is that we can do some regrouping. We can look at these things in a slightly different way. This one, I don't know why that just happened. That's funny. We still have our 3 whole circles, but this right here, if we think about it in terms of an improper fraction, that would represent 6/5. So the one that we borrowed, if you put it out front of your fraction like this, and then convert this mixed number to a improper fraction, you would do 5 times 1 plus 1. And I'm just going to rewrite the whole problem now. 3 6/5, you can see it right here, minus 1 2/5. Now we have enough to subtract with. 6/5 minus 2/5 is 4/5, and 3 minus 1 is 2. And so you can see, take a look at that, try to make sense of that. If you're not noticing it right now, maybe go back and re-listen to this and just stare at that for a little bit. Or you can try the next one. So the one I want you to do is 5 1/3 minus 2 1/2. Go ahead and try that. If you want to draw the circles to make sense of it first, do it, but then come back here. So if we approach it from the borrowing standpoint, we are borrowing from that 5, and then we're going to take that 1 that we borrowed and we're going to add it over here. So one way you could do it is think about 1/3 as 1 1/3. There's the 1 that I borrowed. Now 3 times 1 plus 1 is 3 4/3. But we still need to get common denominator between our fractions. I probably should have even done that first, because I already knew this was going to happen. You should have noticed that you needed to get those common denominators first. Multiplying this by 2 and this by 3 gives us 8/6 here and 3/6 here. What are we going to subtract? 8/6 minus 3/6, which is 5/6, and 4 minus 2, which is 2. And so that regrouping, you have to be careful with that because you need to know what you actually are going to do with that one that gets borrowed. In the next video, we are going to examine multiplication and division of fractions.